Hey, it's Mr. K doing a video for AP Physics 2, and we're looking at electrostatics. Not sure how many topics I'm going to cover in this video, just kind of depends on how long it goes and when I feel like it's a pretty good stopping point. But we're going to try to cover a bit, starting off with Coulombs Law. So from chemistry, you might have mentioned Coulombs Law, the attraction or repulsion of charged particles like electrons and protons. And Coulombs Law is set up like an equation that we already know. K Q1 Q2 over R squared. Q is going to be our charges that are involved. Usually there are two of them. And then the R is going to be the distance between them. And then K is this interesting constant here. It's about 9 times 10 to the ninth Newton meter squared over Coulomb squared. And we need these units for it to work out with this equation. But it's pretty big. The other equation that this looks a lot like is your force of gravity equation when we're dealing with, not just on the Earth, but with any two masses. And that equation is big G m1 m2 over r squared. So look at the similarity between these two. Same setups. Whatever's causing the gravitational attraction or whatever's causing the electric repulsion or attraction, that's going to affect something else that's much like itself. So masses create gravitational field, they affect other masses. Charges create electric fields, and they affect other charges. But it's interesting that it kind of goes down to by the inverse square of the distance. So just keep that in mind. But look at the difference: 9 times 10 to the ninth, and 6.67 times 10 to the negative 11th Newton meter squared over kilogram squared here. So that's a huge difference, times 10 to the negative 11th and times 10 to the ninth. I mean, geez, that's like times 10 to the 20th power. That just shows you that gravity is really weak compared to the electrostatic force. I can move things in the classroom by just charging myself up with a Van de Graaff generator, and I can move strings or balloons or things without touching them. We can bend water without touching it. Think about how big the Earth needs to be to pull something down with the acceleration of about 9.8 meters per second squared at the surface of Earth, and that's significant. I know it feels like gravity is a really huge force to you, but just consider how big of a planet we need for us to feel that force of gravity all the time. And when you think about that, yeah, the electric forces are way stronger. So Coulomb's law says we have the two charges involved. We could have more than two charges, but we need to do the Coulomb's law per charge pair. And here's kind of what I mean. So if I have a charge here, if I've got a charge here, and I've got a charge, let's say, right up here, and let's say all these are positive charges, the two charges that are on the bottom would be repelling each other, one to the right over here and one to the left over here. And so Newton's third law, these two forces would be equal and opposite. Okay, so one is pushing, the one on the left is pushing the one on the right away, the one on the right is pushing the one on the left away, and those two forces are their equal and opposite Newton's third law paired up forces. Now there's another charge here, right? So the charge that's up top, that is pushing away the charge that's over here, and the charge that's down in the bottom right is pushing away the charge that is up top. Again, these two forces are the exact same. The same is true for the charge that's on the left. The charge that's on the left is pushing this top one up and to the right, and the charge that's up top is pushing this charge on the left down and to the left. So if we're looking at this, you can kind of see that this is now a vector problem, and you got to add vectors one dimension at a time. You can't just add them straight up. So you'd have to do a little bit of trigonometry, a little bit of vector algebra, to figure out what the sum of all forces are on each of these different charges. Now, symmetry is going to be a great thing for this class. If you have a symmetrical problem, something with a 45-degree angle, we can use that to our advantage. 30-degree angles are great, and so forth. But for right now, I'm going to skip over the math, and we're going to go on and talk about something called the electric field, because these forces would not exist without the thing that is permeating from all charges, which is called the electric field. So before we totally do that, think about, like, right now you are in a gravitational field. If you have something next to you and you let it go, it's being pulled down by the force of gravity because we've placed this mass in a gravitational field that is caused by the mass of the Earth. So, okay, think about it. It's a field that causes forces. It's a force field. Okay. If I put this calculator here, or if I put this calculator over here, it doesn't matter. It still gets pulled down by this force that's accelerating it at a rate of 9.8 meters per second squared, if that's the only force that's on it. If I put, instead of have this remote control and drop that, it also accelerates at a rate of 9.8 meters per second squared. Although the forces are different, the acceleration is the same. So the field strength I'm putting them in is the same thing. Electric charges also have fields around them. And if I'm looking at this example that we just kind of glazed over a little bit, if I have this positive charge in the bottom left, if I place a charge to the right of it right here, now that charge experiences a force because I've placed it in the field of the first guy. Okay, and this force is going to be repulsive. It's going to push it away. Now, at the same time, the charge that I would place here is creating a field that would push the other guy away. Okay, so and same is true for the top one. The top one, I put that there. The field from both of these two is going to push that top charge straight up, and while that top charge's field that it's creating is going to push these two kind of down and away like this. So the way that we think about fields, if we wanted to draw it, is like so. So let's say we have a positive charge of unknown value, and this charge is going to have an electric field that points away from it in all directions. So I can't draw all directions, but I can definitely draw a handful. So we got north, south, east, west. We've got up and to the right, down to the left, and so forth. So just imagine that we have an infinite number of vectors going in all directions. So positive charge's electric field is considered to be going away from them. Okay. Now, if you have a negative charge, let me draw let's say this is a barrier that no field can pass through here. But if we have a negative charge, well, just by the idea of what negative is, well, you should be able to guess that negative charges have fields going not away from them, but towards them. Okay, and so that's your key difference between positives and negatives. With negative charges, field just goes towards them. They are the total opposite of positive charges. We can draw the diagonals as well, I guess. And so that's kind of the most interesting thing at the moment with charges, and the big difference between masses. There is no negative mass. So masses always pull other masses towards them, whereas charges can do either. They can push away if they're like charges, or they can pull towards if they are opposite charges. Opposite charges attract. So if I were to put these two fields, or these two charges next to each other, and let's take away that barrier now. Let's say we have something like this. If I were to pick positive, negative, and if I were to pick a location like right in the middle, right there, what would the field look like right in the middle of these two charges? And so for the charge on the left, our field would be going, let me use red for positive, our field would be going towards the right. Okay? And if I looked at the negative charge, the field would also be going towards the right in this case. So these two charges are creating fields that point both to the right in the middle, and so we will just add those up. They're vectors. So we have a field that goes to the right. It's pretty strong in the middle of these two charges. Now, if I chose a location not in the middle, but like maybe above middle up here, we can do the same thing and say, all right, this positive charge is creating a field that goes straight away from it. The negative charge is creating a field that goes straight towards it. Okay? And together, when we add those up, we would get some resultant field vector that points just to the right, because you can kind of see how the verticals cancel out. Okay? And so what that tells us is if we take a test charge, in other words, some random positive charge, and if we placed it right here, just to see what happens, it would probably be pushed to the right. Okay? If we put a negative test charge, it would be pulled to the left. It does the opposite. All right, and then lastly, if we were to just run another one and say, hey, what about down here, right below this positive charge? What about that? And so we can say, all right, the positive charge would create a field that points downwards. The negative charge would create a field that points towards it, so like this. But I'm going to draw it a little bit shorter than the positive field. Let's actually lengthen the positive field vector out a little bit more because we're closer to it. And distance definitely matters here. The equation is going to be kq over r squared. That r squared on the bottom means that we get weaker the farther away we are. And so these two vectors would probably point somewhere in this direction in total. Okay, and so what you get when you have positive and negative is you get this field that goes from the positive over towards the negative, like so. And it's unbroken, it's not jagged, it's pretty dang smooth. If I were to look at it, it looks kind of like what is it, like meiosis or meiosis? What is that from biology? And we've got stuff going like that. Okay, and so this is a representation of what the fields look like. So if we wanted to calculate what the field strength was at any location, we would take our equation, Coulombs Law, K Q1 Q2 over r squared. That would give us the force on a charge that we would place somewhere. Now let's just divide by the charge that we place at that location. So if I take F and we divide it by Q on both sides, the charge that's at a certain location, what we get is this equation that's F divided by Q. Okay, that's not really that special, but it's going to take away one of these q's over here. And so we get this equation kq over r squared. What that's going to tell us is how strong the field is at that location, just due to the one charge. And if you have multiple charges in the vicinity, you'd have to add up their vector fields at that location. So by knowing the electric field strength, you could then place a charge there and know the force on that charge. So, for instance, if we happen to know that, let me get some more room here. If we happen to know that we have an electric field that, let's say, points to the right, like this. Let's do one more of these guys. So let's say we have an electric field that points just to the right. We don't really know what's causing it, we just know it's there. And the electric field strength is going to be, let's say like 10,000 newtons per coulomb. Okay. Another way to write that would be like volts per meter, I think it is. And so you're probably going to see both, especially in mastering physics. But that's the field strength. And if we were to put in a charge, let's say like right there, and let's make it a positive charge, and let's make it a 5 microcoulomb charge, what's going to happen to that charge? Well, if you forget kind of what's going to happen with the forces and directions, you can kind of think like at least we might know what causes electric fields. And so if my electric field's going to the right, I could assume that I've got all these positive charges over here it's going away from, and all these negative charges over here that the field's going towards. And so that would tell us that this positive charge that we place there would get pushed away from the left side, and then it would be pulled towards the right side. And so this charge would experience a force pointing to the right. Okay? And to figure out the force amount, well, we would go back to exactly what we just did. Force is going to be equal to K Q1 Q2 over r squared. Well, that's not going to help us out too much, but there was another equation, and that equation was F divided by Q is equal to electric field, which is also just KQ over r squared. So this might help us out. Now, the right side's not going to help us out at all, because we don't have just a singular charge creating this field, we have multiple. But what we do know is that if we have the electric field, that's just force divided by charge. Or, better yet, electric field times a charge that we place into it gets us back to the force on that charge, and that's the one that we should actually be using here. So at the moment I know that the field strength is 10,000 newtons per coulomb, or volts per meter, and I'm going to multiply that by the charge that I place in there, which is going to be 5 times 10 to the negative 6. Okay, so times 10 to the negative 6, that means that my decimal is going to go 1, 2, 3, 4, 5, and 6, so I'll get 0.01, and then we're going to multiply that by 5. So 0.05 newtons of force is what's going to affect my charge that's there, and that's actually quite a bit. It's quite a bit of force. If you want to double check, I kind of want to double check. I've got 10,000, 2, 3, 4, and I'm going to multiply that by 5 times 10 to the negative 6, and I get that 5 times 10 to the negative 2, or 0.05. Okay, so that's going to be how you would figure out the forces on a charge in an electric field. And again, this electric field can be created by maybe two parallel plates like a capacitor or something like that. Now, we're going to go more into this after this video, another video. Like, I'm probably going to stop this in about a minute. But now that we know a force on this charge, if this electric field is constant, which it should be between two charged conductors, then that's force, and it's going to make this charge move. So we would have something that's like a force for a distance. And what is force for a distance? That's going to be work, right? And so this is where it gets a little bit more interesting. Force, again, was E times Q. So I'm just going to replace that. EQD is equal to work done. But let's just divide by that Q one more time. And I got E times D, because we're going to divide everything by Q, is equal to W over Q. Okay? Now that might not mean a lot to you right now, but look at the units of work. The units for work are the joule. The units for Q is the charge. There was something else that we had that was joules per charge, and that something is voltage. So if I know the electric field and I know how long I'm moving in that constant electric field, I can get the voltage value, or the difference in voltage, the potential difference, and that's actually how we get voltage in a lot of these electrostatics problems. I'm going to stop it here. We're going to talk about voltage in the next video, maybe some Gauss's law actually, and then we'll continue on.